Good morning. Let's see. I haven't looked at our exam average yet, but I'm assuming there will be some uh, adjustment that will happen. So you'll probably see that later today. You'll get some sort of notification that your grade will be changed. At a quick glance, it looks like the highest grade is 84. If that's the case, that's what it'll be based off. So that will come later today once I've had a chance to look at all of that stuff in more detail. But hooray, we're done. Yeah. Don't worry. Yeah, this was I told you guys it was a harder exam. No one believes me. Um, but yes, so don't worry about that. Um, with regards to, um, we will have post exam homework for this as well. So you'll have the chance to go over stuff you didn't get correct. Um, I did go in this morning and fix the thing so you can see the answers, since I had forgotten to check that. So you guys will be able to go in now and see what you got wrong and the correct answers that things should have been. So so that'll be adjusted. What else do I have to say? Yeah, I guess that's it. We have one more chapter, which probably will take us. Um, so today, tomorrow, Monday, Tuesday. I don't think we'll need Wednesday, but we probably have 3 or 4 days left of kind of new material, and then we can spend the rest of the semester um, kind of reviewing. So how that can work is maybe we'll have, for the week of the 30th, maybe we'll have a day or two of review there. And then the other day or two we can spend, maybe we can have meetings with your lab groups if you like. So I can take a look at what you guys are doing and say, you know what, this is completely wrong, or yes, this is exactly what I would have done, or whatever. Get you some feedback on those so that it's not completely out of the blue. So maybe that's what we'll do on the week of the 30th. I've gone ahead and decided that our final exam will be on the 8th and 9th of December. So you'll have 48 hours to take it. It doesn't allow access to chapter 11? What? Really? Let's have a look. Okay, if that's the case, that is a problem, isn't it? Acid-base chemistry. Um, I see it on mine. Like, when I go to the chapters and go to 11, I do see. Ah, what the heck? Yeah. So I see all the acid-based stuff here. I'll go ahead and shoot them an email, see what's happening. Okay, I'll go see what's happening, Sherry. We'll figure that out. Um, so yeah, we'll see. Maybe there's some like random thing that's blocking it or whatever. Who knows? Okay, but I will. Cool. I will let them. I'll contact the publisher and see what's happening there. Yep. Cool. Okay. Well. Then. Well. Anyways, we'll see. That this stuff is. There's a few new things here. We're kind of going to be working on identifying acids and bases, and then kind of looking at strong acids versus strong bases, or strong acids versus weak acids, and same for bases, and then kind of looking at how we quantify acids and bases as well. So it's not too much new stuff here. So um, yeah, we'll get this going here. Cool. So I think I was talking about the final exam. Yeah, so you'll have 48 hours to take it between the 8th and 9th. I wanted, since your projects are due on the 6th, I wanted to give you the 7th off so that you, could rest a little bit, because I know, okay. So yeah, Lamonda, I'll check with the publisher, see what's happening there, because that's something strange. So maybe there's just like a button that they need to click or something. So, okay, yeah, I'll check on that as soon as class is over. So yeah, I'm gonna give you the 7th. You guys can rest and I guess deal with your other finals maybe, or spend the day shoving information into your brains, whatever you want to do on that. And then you'll have the 8th and 9th to take the exam. So it'll be about twice as long as a regular exam. So I think it's about 50 questions and 2.5 hours. And so it'll be done with the Proctorio again, but just like before, you can have as much crap as you want in front of you, your calculators, your cats, your screaming children, totally okay. So just like that. Okay, so so that's kind of our plan for the rest of the semester here, and then we're done. Hooray! So you'll probably have just one more homework assignment after the post-exam homework, and then and that'll be it. So hooray! Exciting times. Alrighty, well, let's get into it then. Let's start talking about acids and bases. So previously we talked about acids as having, they have H plus and are aqueous. That's kind of what we've defined acids as right now. And so we're going to see that this is a pretty narrow definition that is not going to work for a lot of things. So we're going to see that this corresponds to what is called the Arrhenius acid definition. And these are things that when placed in water, they release H plus. And so we're going to see that an example of this would be something like HCl. If we were to put this in water, we'll just go ahead and we'll pretend it's a reaction here. We would get this. This part here, hydronium, for us is the same thing as saying H plus. It's an H plus that's stuck onto water. So in reality, it is indeed stuck onto water, but we're going to see it's just a lot easier for us to talk about H plus as if it were one thing by itself. So this tells us that HCl is going to be an acid. It's something that forms H plus when we put it with water. And so that's kind of this definition that we've been working with so far. And for bases, for the Arrhenius base, they produce OH minus in solution. And so we're going to see that something like NaOH would be a strong base. It's going to just break up into the ions, right? It's an ionic compound. So just like we did with our net ionic equations, we would break those into ions. We could also see that certain other things could be bases, like ammonia. where it would form OH minus as well. But these are kind of old and not so great definitions, because we're going to see that things can act as acids without having to be aqueous. Things can act as bases without having to be aqueous. And we could also have acids and bases that don't involve this hydroxide and H plus thing happening. So we're going to see that, you could have different solvents. You could have things that are not in water at all, just plain old compounds reacting as acids. So this kind of definition is passé. We don't really use it as much. So we have a better one, which is called the Bronsted Lowry acids and bases. And this one tells us that acids, these ones are proton, which is the same thing as H+. Remember, H+ has no electron, so it's just a proton. And so a Bronsted-Lowry acid will be something that gives away a proton during a reaction. And a base, on the other side, will be a proton acceptor. In a chemical reaction. So where the Arrhenius definitions kind of talked about things in solution, just how they behave by themselves. This sort of definition talks about how they behave in chemical reactions. And that's going to be more kind of applicable to what we want to look at here. So if we take a look at that same reaction above, I'm just going to ignore the states here. It doesn't really matter. We're going to see that we have NH3 becoming NH4 plus, and we also have H2O becoming OH minus. You'd be able to choose these by looking, okay, what's the most similar to each other? Which product is more similar to the reactant, to which reactant. So, of course, we can see that the one that has nitrogen should be it's kind of the same compound, and we're just throwing a proton on. And the one with oxygen, we're just taking a proton off. So we're going to see here that this is going to be a base. We are accepting an H plus in the reaction. So we're going from having 3 hydrogens to having 4 hydrogens. So we have gained a hydrogen. So this is very similar to stuff like oxidation and reduction, right? Instead of messing with electrons, now we're messing with protons. And here we're going to have our acid, which is going to be donating an H+. So it's going to lose an H+. So very similar to our oxidation and reduction type idea. But now we're working with H+ instead of electrons. And this one is a little bit easier to see. We don't have to actually do any oxidation number stuff. We can see very clearly that the ammonia has 3 protons, 3 hydrogens rather, and the ammonium has 4. So we can see that it has gained an H+. We see that water has 2 H+, and hydroxide has 1, and so it has lost 1. So we can do another example, perhaps. How about we do... We can apply this to, kind of any standard acid-base problem. And so if we were to identify the acid, we always want to kind of look at the negative part, the anions. So we're looking at the anions here, and we're trying to look at what they've turned into on the opposite side. So we will always want to look at the anions. And so if we, oops, let's look at, I should probably do this in green instead. So if we look at the products here, which one of these is most similar to sulfuric acid? Which one has the same anion as sulfuric acid? Which one of these do we think is going to be more similar? Yeah, right. So it'll be the sodium sulfate, right? So we're looking and we see that we had we are going to see, well, here, I'll put the sodiums in there. Sodiums don't really matter, but let's go ahead and put them in there anyway. And then we're going to see that the other one is kind of what the hydroxide looks like. So we've gone from hydroxide to water. So looking at these, we see that this has lost or donated H plus over the course of the reaction. It had 2 H's to start with. It now has 0 H's. If we look at sodium hydroxide, that had 1 H, and now it has 2 H's. So this has gained H plus. And again, we always look at the anions because H plus is positive, right? So we're always going to be looking at the negative thing because that's going to be where the H pluses would be attached to. And so we would say, therefore, that sulfuric acid would be our acid and sodium hydroxide is our base. Let's look at another example. How about something like this? Let's look at this one. Actually, let's make this... No, we'll leave it as is. So, let's take a look at some anion. Yes, let's take a look. We see we have a very obvious kind of pair there. And our other pair is going to be these two. So we can see very clearly that this blue one has lost H plus, and the green one has gained H plus. So remember, gaining is going to be your base, losing is going to be your acid. Yes. So I remember I did tell you that how many months ago now. So yes, I'm glad you have remembered acetate there. Let's take a look at this one then. So again, we are looking at the anions, seeing what changes there. So we're going to look at this anion and see which compound that corresponds with. That should, of course, be this. Again, you're looking for what's the most similar from left to right. And, of course, then the other pair would be the nitrate one. So we can see here that the blue one is going to be gaining H+, so it's a base. And then this one is losing H+, it's an acid. So hopefully this is not too bad here. If we noticed, if we take a look at these two, they're very similar, right? All we've done is swap an H for a sodium. If we look at the top one, that one acted like an acid. But the bottom one, it acted like a base. And so we have fancy terms for these. We call them a conjugate pair. So this would be, for example, we're going to see that this will act like an acid, and this one acts like a base. And, you know, they're essentially, at their core, they're the same, right? One just has a hydrogen stuck on. So this one we could call in a reaction. Here, let's go ahead and let me copy the reaction from above. Yes, exactly. So remember, anything that's not H would just be some sort of counter ion. So sodium, potassium, lithium, whatever. Something that's just there for charge balancing. It doesn't actually stick onto it. Like with acetic acid, we know it's a weak acid. Like 99% of acetic acid stays with the H on it. But for something like acetate, we would need a full counter ion. So that could be sodium, barium, silver, whatever, some sort of positive thing on there to charge balance it. But as soon as we put that in water, it's going to separate, right? So we're going to see, yeah, it would be anything besides H plus for sure. Okay, so I did not intend to kind of copy all the extra colors here. But we're going to see, we remember we've identified this as the acid in the reaction. The term then we apply for the opposite one is the conjugate base. That's the one in the product. Your acid will turn into a conjugate base. So the acid, as it loses its proton, becomes a base because it may want to come and take that proton back, or it may want to take it from something else if you were to apply it to a different reaction. We're going to see that a lot of these acid-base reactions, if they're not involving strong acids or strong bases, are going to be reversible, meaning they're always kind of going back and forth. And so the proton is just moving in between the acid and conjugate base all the time. So, by contrast, the water here, which we saw was acting like a base, it turns into the conjugate acid. And we're going to see that if we were to take either of these products and put them into new acid-base reactions, that they would act as what's written here. So we would see that H3O plus ammonia could turn into something like this. So notice here, this is acting like an acid. And then this would be the conjugate base. Oops. So it all just depends which direction your reaction is going. But these things kind of occur as a pair. So we're going to see that water and H plus are a pair. Water and OH minus are a pair. It's just going to be the opposite one. So we're going to see that it just depends what you're mixed with. So acids will react with bases and vice versa. So they don't react with each other typically. So, and then here we would have the base and its conjugate acid. So the conjugate thing is just what's on the product side, whatever your acid or base turned into. So your acid will turn into a conjugate base, your base will turn into a conjugate acid. All right, so there's our terminology here. I'll just write that in a sentence. An acid will turn into a conjugate in an acid-base reaction. So, and then it's just the opposite if we were to put base instead. So we're going to see that a base will turn into a conjugate acid. So that's a very good question, and that's something that we're not necessarily going to cover in this course, but it essentially deals with how stable these things are. So ammonium is more stable than hydronium, so it is going to move that direction. However, this is always an equilibrium. So yes, oxygen is more electronegative for sure, but this essentially gives a positive charge to oxygen. And oxygen being more electronegative does not want a positive charge. Nitrogen being less electronegative can accommodate that positive charge a little bit more. So that's the reason for that. But again, these kind of just go back and forth. So it just happens. So these are always kind of in balance with each other. And so it really just depends on the stability here. Yes. So one thing that's very important to note is that strong acids or strong bases have extremely weak conjugates. So for example, if we did this reaction, we've done it already. HCl we've determined is a strong acid, right? We've already learned that in, our solutions chapter. Its conjugate base is chloride. And we're going to see that if we were to try and flip this reaction around, this would not happen because chloride is too weak of a base to be able to take that back. So for anything that's called a weak acid or weak base, we can have these reverse reactions happening. But for strong acids and strong bases, their conjugates are way too weak to do anything. So a weak base is going to have a very hard time trying to gather a proton. Usually these mean that they're very stable. So chloride is super stable. We know that. It's got its full octet. Everything's happy. You know, it's a preferred charge. You know, it's going to be hard to mess with that. If we look at a base, actually, it's not really going to change anything. Let's put this with some sort of acid. We can see here that the conjugate acid is going to be a very weak one. So water by itself does not necessarily act as an acid. So if we were to put water with a base, you know, it's not really going to react very much. Let's have a look. If we put water with a base, what are we going to get? We're going to get this. Nothing really changing. Let's use some color here. We'll make this a little bit more obvious here. We'll make this HOH. So through standard double displacement, you know, we would now mix sodium with that hydroxide and this hydroxide with that H+. We would get the same thing. So yeah, a proton has moved, but we can't really tell a difference here. So water is a very, very weak acid, weak base. So the lesson here is that your conjugates are going to be not so good at being acids or bases if it comes from a strong acid or strong base. We're going to see also that metal cations are typically very weak acids. Extremely weak. So weak that they're not going to do anything. But the idea here is that, you know, it's the remaining bit. We know that if we put sodium chloride solution out there, there's no acid-base thing happening. That's just salt dissolving in water. There's no acid-based chemistry happening with that. We know that, of course, if we were to combine sodium hydroxide, hydrochloric acid, we would get these two, which are both very, very weak. So we have a strong base and a strong acid. And so we have a very weak base and a weak acid. Very, very weak. So that's why we don't mix sodium chloride and water, or rather when we do mix sodium chloride and water, we do not get our reaction to happen in the reverse way. This does not happen. We don't end up making our strong acid and base again. Just too weak to do anything. All right, so that's the idea here. Let's review our strong acids while we're here, I suppose. So strong acids, again, have very weak conjugate bases. Our strong acids were these three plus sulfuric acid, nitric acid, and perchloric acid. So these were our 6 strong acids. And so we're going to see here that these conjugate bases are very, very stable. In chemistry, stable means not reactive. So once you have Cl-, it's happy, it's done. It's like a noble gas. It's not going to do anything unless we give it some really crazy reaction conditions. So once we've formed chloride or sulfate or nitrate, they're happy. They don't need to react anymore. So that would be these would be the conjugate bases here. These are extremely weak. So these are our conjugates here. These are very, very, very weak bases. So weak that, we're talking 10 to the, I don't know, like 20. So some crazy amount of, preference for these things to be as anions rather than to have the hydrogen on them. So very weak if they're made from strong acids. Our strong bases, we have just a few of those. It's kind of our group 1 hydroxides, and to an extent we have our group 2 hydroxides. And that's kind of it there. We're going to see that these have very weak conjugate acids. So the conjugates there would be and notice again all of these ions are, in their happy place. Potassium has lost its electron. It is very stable. We know from our chemical reactions potassium is pretty much always a spectator ion. These things don't do anything once they're kind of there. So at least acid base wise. So again, same thing here, just the opposite. And so we remember that strong acids or bases completely ionize. In solution, right? They will just completely separate. So we're going to see that something like HCl, which is a strong acid, will break 100%. Something like acetic acid is about 1% ionized. So we're going to see that something to be called strong or weak is just the nature of the chemical. So it doesn't have anything to do with how much concentration it has. We're talking only about the identity of the compound. So this one is going to be a strong acid, and this one is a weak acid. And I guess if the thing is not working for you, let's go ahead and look at the video demonstrating this so you can see that I'm not just lying to you. Because I'm sure all of you believe that. So, okay, let's go ahead and let me find the video for us and we can take a look. Is this the right video? No, that wasn't. Okay, hold on, let me find this silly thing. Oh, go and figure, the video is not loading. But we're going to see here, once the video does load, I'll contact them and we'll see what's happening with that. That you're going to see that if we were to do our conductivity experiment, if we put, our electrodes... So it just depends on stability. So acetate is not as stable as Cl-. So it's just a matter of how well... Yes. So it's a matter of how well they can accommodate that charge. So we're going to see here that... So we're going to see here that Cl-... It's a very good question. We're going to see here that the chloride is going to be much better at accommodating that negative charge than the oxygens would be. If we do the Lewis structure for acetate, we do indeed have a negative charge on an oxygen, which is a good thing. Um, the only way to do that is to look at this list. So, I mean, technically, there are ways that we don't teach in this course that you'll learn in 113. Here, but let's see. There are definite charts that will show you exactly kind of how strong things are versus each other. If I could get this silly thing to load. Okay, here we go. So, for example, this crazy chart has a whole bunch of different acids. What we want to understand here is there is a value called Ka, which is, again, not something we're going to talk about in this course, but it essentially is the degree of how far something will ionize. Oh, gosh. Ew, it's blurry. Oh, no, it's not. Okay. Okay. So if we look at some of these, we're going to see that all of those strong acids that we mentioned are all going to completely dissociate. And that the conjugates are ineffective. As we go down with other acids, we're going to see that those, this is saying that basically, 0.16 would be the kind of how much is ionizing. So as we go down here, these are all getting weaker and weaker and weaker. Hydrofluoric acid, is 10 to the minus 4. So these things dissociate less and less and less. So these are all experimentally determined. So there's not an easy way for you to just go and say, oh, oxalic acid is stronger than nitrous acid. There's no easy way for you to do that without having information like this. So this sort of thing would be stuff covered in 111. So we don't really worry about that here. For right now, you just have to remember that we have these 6 as our strong acids. Okay. We don't normally consider chloric acid, but I guess this one wants it to be. So yeah, lists are nice. I like data tables. So yeah. Okay. Speaking of which, if we look at acetic acid, this is acetic acid, right? Put the H on there. Just a distinction to make. This H here is the ionizable one. I can spell ionizable. Whereas these 3 H's do not ionize. We're going to see that it's predominantly hydrogens that are on oxygens that are going to be ones that will be ionizable, that will act as acids. The H's that are on carbon there don't react as acids. So, we saw that. I mean, if you want to look at that chart, acetic acid is about 10 to the minus 4. The one on carbon is about 10 to the minus 50. So, not going to react as an acid. They don't leave there. And this is because OH bonds are relatively weak. And typically, we're either going to form a new OH bond, or we're going to form an NH bond, and an NH bond is even stronger than an OH bond, so that's why these things are going to form that way. So we're going to see that many acids are oxyacids. And so we're going to see that those are just ones that contain oxygen. And you know what? Let's just go ahead. Let's pop up that list again. if we take a look at this list here, we see that like every single one of these has got oxygen in it, except for hydrofluoric here, it looks like. But everything else, look at all the oxygens. So we can see here that most of these acids are going to be oxy acids. And those are going to have hydrogens that are bound to oxygens. And so those are going to be where we're going to see these hydrogens coming off of. So CH bonds are extremely strong and will not ionize. So they're not going to break apart. Whereas the OH bonds are relatively weak, so they can go ahead and, dissipate. They can break apart there. So, anyways, I will kind of explain our strong thing in a bit more detail here. So, suffice it to say, if I had 6 molar acetic acid versus 0.01 molar hydrochloric acid, we're going to see, or you would see, if I could get the video to load, that this one would be super bright. And this one would be dim. So because the weak acids are weak electrolytes, they do not break apart very much. So even though this is more concentrated, we actually have less H plus in solution. So it's more concentrated, sure, we have more of it dissolved in our water, but there's less H plus floating about than in the HCl solution, because the HCl is a strong acid. So this is less concentrated, but has more H plus, because all of it is going to break apart. Whereas the other one, only a small little bit is going to break apart. So, we saw that the Ka for that was 10 to the minus 4. So we're going to see that, we're talking about 100% dissociation versus 10 to the minus 4. 1 is obviously the bigger number, right? So it does not matter that what your concentration is. A strong acid is always a strong acid, and that is only based on the identity of the acid. So acid strength. Okay, I'll fix that. Wow, I can do this, I swear. There we go. Does not depend on concentration. So strong acids will always be strong, weak acids will always be weak. So nothing has to do with concentration here. So perhaps tomorrow, once we can get the video to show, I'll show you actually taking these electrodes and putting them in, and we'll be able to see that this acetic acid, even though it is more concentrated, is not strong. Concentration and strength, while we may want to think about it that way, it does not work for acids. So the correct way to kind of classify these is you would say the 6 molar acid is more concentrated, but the HCl is the strong acid there. So there's nothing to do with concentration on this. Do we have any questions so far, by the way, with this stuff? So I guess we've talked about strong acids before, so this is not necessarily new. But any questions so far? Because we're pretty much like halfway done with this chapter, so I don't want to feel like we're zooming through it, but you know, the fun stuff actually begins when we start bringing the math in, of course. That's always the best. How do you know something is a salt? Oh, easy. So, in chemistry, the word salt means soluble ionic compound. So that when you would refer to your solubility rules. For example, like sodium nitrate would be a salt. Potassium acetate is a salt. Copper 2 chloride is a salt. So it's just a soluble ionic compound. That's it. Yep, so that would just be, you'd refer to your solubility rules and see what's soluble, and that would be what a salt is. All right, typically salts are typically also overall, no, let me not say that. These are typically, man, I don't want to say this. This is what I'll say. Excluding hydroxides. So something like sodium hydroxide we do not classify as a salt because that one is a base. It is a strong base. We do not consider it. Here, let me write hydroxides a little better. I realize that's kind of squished together. So salts are typically produced in acid-base reactions. You would never produce NaOH in an acid-base reaction. And so that's going to be kind of our exception there. So something like sodium hydroxide, lithium hydroxide, potassium hydroxide, whatever, those are not salts. But pretty much everything else is. Sodium sulfate, sodium nitrate, sodium carbonate, sodium, selenide, whatever, all of those are salts. So anything that's not a hydroxide there. Okay, cool. Our next, let's see, we've got 7 minutes. I don't know that I want to start the math stuff right away because I don't think we're going to have enough time to really get anywhere with that. So, yeah, let's go ahead. We'll end here for today. And so tomorrow we'll continue with our acid-based stuff. Thursday, if you want, we can do our review. Perhaps that's a good thing. And then, next week we'll continue as normal. So, cool. Any kind of questions that are still there? All right, well, with that, I guess I'll see you tomorrow. So, have fun.